Now we're going to look at ways we can evaluate a discriminant function when we have more than two groups. So far we've really focused on cases where we only had two groups, and we looked at how we can sort of classify between the two groups as much as evaluate the discriminant function itself. So how can we go about separating the three different groups, or more than three different groups? One hint is that we can sort of rethink this in terms of a canonical correlation framework and use some of those methods that we've learned. So the first thing we're going to want to do is find the discriminant function that maximizes the difference between each of the three group means. So that means that we want the largest possible differences between each group mean and each other group mean based on our discriminant function. Next, we're going to find the function that maximizes the difference again, but this time also produces values that are uncorrelated with those produced by the first discriminant function. We'll call these the canonical discriminant functions. We can think of this procedure just like a canonical correlation in a sense, where we are using dummy variables on the y side of the equation and continuous data on the x side. And really in canonical correlation, that doesn't matter. That's just the way we can think about it here. So if that's how we're thinking about it, how many different discriminant functions can we get from our data? So how many, as a review, how does the number of variables determine the number of canonical correlations? And also, how many dummy variables do we make for a grouping variable when we do an ANOVA in the regression framework? So in a canonical correlation, we have the number of canonical correlations we get is the minimum of the number of variables on either side. And for grouping variables, we can make G-1 dummy variables. And so in discriminant analysis, we can have the minimum of P, which is the continuous variables, and G-1, which is the number of groups, discriminant functions. So to get our discriminant functions, we can start to think back to what we've learned about one-way MANOVA. When we did our one-way MANOVA tests, we looked at three different matrices and compared them in different ways. These were the SSCP matrices for between, within, and total. And this is just up here for review, which shows how we computed them. We can get Wilks lambda as the ratio of the determinants of the within to total matrix. Or alternatively, we can get it as the product of 1 over 1 plus the eigenvalues of B times W inverse. These are two different routes to go and compute Wilks lambda. So far, we've used lambda to test whether there are differences between the groups on some linear combination of the variables simultaneously. But another way to think about this is that it's also consistent with discriminant analysis in that it's testing the separability of the G groups. So it's testing whether we can actually discriminate between the groups for our under our discriminant function. It also turns out that our discriminant functions are defined using this BW inverse matrix. So we take the associated eigenvalues and their eigenvector pairs for the first however many canonical discriminant functions we have, and those represent the coefficients for the ith discriminant function. So it's the eigenvectors represent the coefficients of the discriminant function of this BW inverse matrix. And keep in mind, R is going to rescale these in this particular way. So when we looked at canonical correlation, we used lambda to test the significance of the canonical correlations as the product of 1 minus each of the canonical correlations. And then that tests the first, and then we could iteratively go and test each subsequent canonical correlation, essentially by deleting the first one, and then testing the remaining canonical correlations. So here you see we start with the second test, we start at 2, and then we would keep going and start at 3 for the next test until we reach a non-significant result, at which point we conclude that all subsequent canonical correlations were not significantly different from 0. So we can apply the same logic to discriminant analysis, just computing lambda the same way, where all we're doing is deleting one of these eigenvalues, and we can iteratively test the significance of each canonical discriminant function by starting out by testing the product involving all of these eigenvalues. Then we start with the second one until we reach a non-significant result. So there's nothing really new here mathematically. I've shown you the math behind all of these procedures at one point or another in this class, so I'm not going to go into it here. We're just going to go into the R. And so this example is an expansion on what we've seen, what we've been looking at, where we're looking at how temperature and oxygen predict whether someone is healthy or sick, except this time, instead of just looking at COVID, we're going to look at COVID or flu or healthy. I mean, once again, this is simulated data. So these are the means that I simulated the data from. So for COVID, the mean temperature was 100, oxygen was 96. For flu, the temperature was a little bit higher, but oxygen was not quite so low. And this should be not COVID, it should be healthy. I will fix that when I fix these up, but this should be the mean vector for healthy is 98.6 and 97.5. So flu has the highest temperature, but it has a similar amount of oxygen to people who are healthy. COVID has a high temperature and much lower oxygen. So that's the parameters that we're simulating our data from. And we're going to see if we can use this to differentiate between our groups and our simulated data. This is the shared covariance matrix. I have no idea how realistic these values are. It's purely a hypothetical example. So let's see how this works. So here's a look at our data. We see we have 100 observations for each class. So we can do what we did last week and use the LDA function from the mass package, or even the QDA for quadratic discriminant analysis, but that can't be associated with MANOVA because it means that we're not using the equal covariance matrix assumption. And so this might be useful if we wanted to split the data up in some different ways and do some classification. Like we might say, I want to compare healthy people to people who have flu or COVID, or I want to compare COVID people to people who don't have COVID or something like that, create some binary classification. But in terms of assessing the overall discrimination for the G equals 3 groups, it's not very informative. So alternatively, we can just run a MANOVA like we've learned, and this is essentially testing the separability. So I'm just going to do MANOVA with temperature and oxygen on status and get my result here. And so this would indicate that the data is separable. So we can report this as the data are separable based on oxygen, and the 3 groups are separable based on oxygen and temperature, do my statistical report. Or another way to frame it is that at least the first discriminant function separates the groups. And so how many discriminant functions are we going to have here based on the data structure that we have? Well, we have P equals 2 variables and G equals 3 groups. And so we're gonna have a minimum of 2 and 3 minus 1. So they're both 2. So we're gonna have 2 discriminant functions. So another way to get the discriminant function is to use the Candice package and the Candice function. We can use this on a MANOVA object, and this will estimate the canonical discriminant functions. We could also use this to assess the discriminant functions in different ways, but first we'll just fit it, and here we pull out the coefficients, and you can note that these match up to when we did it with the LDA function and the mass package. So this is the same result that we got from that. So if we print the Candice object, it's going to give us a test for each discriminant function. It's slightly cut off here at the bottom, but you can see that we have a significant result for both discriminant functions based on our likelihood, our test statistic, which is going to be the Wilks lambda, and then the test that we described before. So we can also check the summary output to evaluate some features of the significant discriminant functions. We'll usually focus on the significant ones. So the summary output is going to give us three things: the proportion of variability explained by each discriminant function, the means for each group on each discriminant function. So this is the mean for the linear combination of the variables for that discriminant function for each group, and then the standardized coefficients for each discriminant function, which are, again, as before, are much easier to interpret than the unstandardized ones we've seen. So we are going to specify which ones we want to interpret with the MDIM argument, the number of dimensions argument. So here, both were significant, so I can set MDIM equals to 2, but if you had 5 discriminant functions and 3 were significant, you probably set MDIM equals to 3 and just interpret those first 3. And so here's the code. It doesn't all fit on one page, so we'll see it on the next page. And so here's the summary output here. So here at the top, we see some information about how much variability each discriminant function explains. So we have like this CAN-R square is like an effect size. It's like sort of like eta squared. And then the percent of variability explained in the data, and the cumulative percent of variability explained in the data. So then we have the means for each group on from each discriminant function. So we see that in the first discriminant function, we get extremely low negative values for flu and very high positive values for healthy, and then COVID sort of in the middle. So it is separating the 3 groups out quite a bit, and that none of these are very similar to each other, but we're really separating flu from healthy here quite a bit. And then here based on the second function, we see that COVID is positive, and then both flu and healthy are negative. So this looks like it's separating out COVID quite a bit more from the other 2 classes here. And then we can look at the coefficients to see which coefficients are driving the function. So we can see here for the first function, temperature is really driving it. And so this really makes sense with what we know about the estimated parameters. We know that we estimated that flu would have the highest temperature and that healthy would have the lowest temperature. So it makes sense that temperature is really driving this, but we're getting some information out of oxygen here as well. But for the second one, we see that oxygen is really driving the second one, which is why we're getting COVID separated out really well by the second discriminant function, because we know that that was the big thing that was different about COVID, was the lower oxygen. And so the way to interpret these is to look at the standardized coefficients to determine which variables drive with function, which functions as I just described, and look at the differences in the class means to determine how well each discriminant function is separating the different classes from one another. And so this is sort of a summary of what I said before. I won't linger here right now, but this just repeats the interpretation I gave before about the coefficients and the class means on the discriminant functions. So another thing we can do is we can look at the correlations between the results of the discriminant functions and the original variables, and that this is another way to evaluate how highly correlated each variable is with the discriminant functions. And so here is the scores are the results of the discriminant function. So this is what would happen if you multiplied the 2 coefficients by the 2 variables for each observation. So that's the first canonical discriminant function, and then we have the second one, which would be the second function. And so we can correlate this with the original results. Here, I'm just making sure to drop my grouping variables. So the grouping variable was the third variable in the original data. It was the first variable in that scores. So we see here in the scores, it's the first variable. And so here we can just sort of interpret these correlations. We see that temperature is very highly correlated with the first discriminant function, and oxygen not so much. This is consistent with what we saw before. And then for the second one, we see that oxygen is almost perfectly correlated, whereas temperature is still correlated, but this is really almost exactly just oxygen. And so this is just repeating what I just said. The second function is really just almost equal to negative oxygen, and it's also still correlated with temperature because temperature and oxygen are correlated. So one last thing we can do is we can plot these functions and get a sense of where the data lies on the axes. So in this case, we have two canonical functions. So it's going to plot the x-axis as the first discriminant function and the y-axis the second one. If we have more than two, you can select the functions you want to plot with the which equals. And then it's also going to show you the proportionality of variability explained by each function. Then it's going to place the means of each group on the plot, and it's going to show vectors representing how the discriminants are related to the canonical functions. So here is the plot. So we see here that the first discriminant function really is separating out the flu, which is very far to the left over here, and then COVID and healthy are sort of in a similar location further to the right. And then the second discriminant function, on the other hand, has COVID very high up here, whereas flu and healthy are much closer together down here. We also see that temperature is sort of at an angle to both axes. So that means that it's providing information to both axes, whereas oxygen is really pointing down towards this second axis, the y-axis. So the second discriminant function is really being driven by oxygen. And so this is, again, what I just said on the previous slide, just the interpretation. And so what a lot of this really highlights is that discriminant analysis MANOVA are sort of like a hand-in-hand technique. They're really based on the same mathematical concepts. The difference is the purpose and what you're looking to do with the results. So if you're interested in really testing fixed group membership, for example, if you did an experiment and you want to see how the treatment or control groups differed, you might be more interested in thinking about the MANOVA that we did earlier, the type of MANOVAs we did earlier in the semester. But if we're really just interested in seeing how existing groups differ and seeing if you can sort of identify group membership for existing groups, then you're probably more interested in the discriminant analysis approach. But either way, these procedures can go hand in hand. And in practice, you can use both perspectives to sort of interpret your results. And so they're really a complementary and sort of holistic way of looking at this type of data.